All right, everybody, thanks so much for being here. Welcome to another AMS Weather Band webinar. We're really thrilled that you could spend your afternoon with us. We're really absolutely excited to have Deke Arndt, the Chief of the Climatic Science and Services Division at the National Centers for Environmental Information and AMS Council member with us today to talk about the new climate normals. So I'll hand it over to him in just 1 minute, but first of all, I wanted to say that we will be taking questions, or he will be taking questions throughout the presentation. So if you do have any, please put them into the Q&A box. There is a Q&A button at the bottom of your screen there. So if you could put them into the Q&A rather than the chat, that allows us to keep better track of them. And people can actually vote on your questions and prioritize them. So if you could, again, just use that Q&A box, that's super helpful for us. And I will be keeping track of those throughout the presentation. Afterwards, within the next day or two, this will be posted to the AMS Weather Band website at amsweatherband.org for members to view on demand. So again, we invite you to continue the conversation after today in the community as well. So with all of those caveats, thank you again, Deke, for being here to walk us through the new climate normals. We're really excited to have you and to learn more about what that means. And what that means for us going forward. So I will hand it over to you. And again, thank you all for being here.
Thanks a bunch. Very much appreciate it. Thanks, Tiernan, for having me. Thanks to the AMS Weather Band for having me. Thanks for everybody for being here. It's a really cool program, and it's nice to share. You know, we all share the weather and climate that's around us, so it's only natural that we share between us as well, kind of what we know and observe and see, and think we understand about the world around us. And really salute your curiosity into jumping into more weather and climate stuff. So with that said, I'm probably going to share my screen here. I used to make fun of my dad because he couldn't operate the VCR, and now, you know, technology is just as hard. So there we go. Looks like it works. I am Deke Arndt. I'm the chief of the Climatic Science and Services Division. We're one of several kind of climate information and climate services pieces within the agency NOAA, National Oceanic and Atmospheric Administration. You probably know the Weather Service. If you're a weather fan, you know our Weather Service very well. So I'm in a slightly different part of NOAA, and we'll share a little bit about what we do, and particularly our publication of the new normals. And it's really cool that we have a weather band meeting today right outside my window. Just had a really amazing cloud to ground lightning strike. Surprised me. All right, so I cannot see the chat, but I worked with Tiernan beforehand. If you have questions in the chat, please do bring them up. And when they kind of get a critical mass behind them, I think Tiernan is just going to jump in and we can talk Q&A. So, all right, so what is the new normal? So we'll just talk a little bit, introduce kind of who I am, where I'm coming from. We'll jump into what are normals, kind of why are they used, why do we have them, and then what are the new normals that we just published this spring, and kind of what are they saying to us, and then you know, why does that matter? All right, so I'm coming to you today from Asheville, North Carolina. That's the headquarters of the National Centers for Environmental Information. We're a combination of 4 campuses, an Asheville, North Carolina campus that focuses on weather and climate data, a Stennis, Mississippi campus that focuses on coastal data, a Boulder, Colorado campus that has a lot of geomagnetic and geospatial and geological data, like magnetic fields, gravity, cool stuff like that. Our paleoclimate unit is actually in Boulder as well, the people that study tree rings and capture that data. And then Silver Spring, Maryland, where a lot of the world's ocean data ends up. So NCEI is kind of a composite of these 4 approaches, collections of the world's scientific data, and Asheville happens to be the weather and climate piece of that. A lot of people come to retire in Asheville, and it turns out a lot of weather data comes to retire in Asheville. And to just go a little bit deeper into that, so this is just a kind of a picture of what we do. That's our building there on the right, and what you see is a typical weather forecaster explaining the numbers and kind of going over current conditions for their part of the world. And that data ends up in our building. The observations that are used to help support weather forecasts and that we use to protect lives and property, and the meteorologists in AMS and elsewhere kind of use in their day-to-day operations. All of those observations end up in our building, or technically in the cloud, managed through our building. And they're married with some, much older observations. We have weather observations, direct measurements dating back to the 1700s by, Independence era folks. We have some documents from Thomas Jefferson, and we have paleoclimate records out in Boulder that again indicate conditions hundreds of thousands to millions of years back. All of that kind of works together. There's a reason to spend a few precious minutes kind of describing how all of that stuff ends up here together, because it's going to come into play when we talk about normals. In the era before we had computers and we could digitize data and share it over the internet, that observer that you see in the black and white photo, that's a Nebraska rain gauge from the late 1800s. That data was transcribed by hand, written onto paper, literally mailed to the weather forecast office through the USDA at the time, and wound up ultimately in our archives as paper records. And so we've had to go back and redigitize that data, key it in, make digital numbers out of the handwritten numbers. So all of that data can kind of come together, and technologies change over time. And one of our roles is to try to help marry today's information with that of the past, and increasingly that of the future. And how do today's observations fit? And how do we account for the fact that thermometers and rain gauges and satellites have all kind of come online and evolved at different times? So that's one of our roles that feeds into our mission. And then just very quickly about me, I grew up in Oklahoma. I worked in Oklahoma for many years. I'm a meteorologist by training. So I went into climate for the most noble of reasons, which is I needed a job, and there was a drought opening in Oklahoma. And I worked on drought, my first job out of school, and kind of fell in love with the slower pace and the relationship that people have with things that happen on the climate scale, particularly in a state where agriculture is so important. Day-to-day weather is important. Definitely everybody pays attention to it. But what happens over weeks and months and seasons is really important in the agricultural space. And the relationship that the growers especially had with the climate kind of veered me into drought and climate services and climate science. And that's where I've been for about a quarter century. It's been wonderful, great line of work to be in. That eventually led me, as many apply, my technical term is applied climatologist. I'm someone that applies the principles of climatology to kind of real world and data problems. A lot of applied climatologists want to end up at NCEI in Asheville, and I was lucky to get on board here in 2009 as the chief of our climate monitoring branch. And they're kind of the scorekeepers of the global climate system. They calculate the global temperature and where's drought happening and all of that kind of stuff, which is a wonderful job. All right. So just some, call them navigational aids, just some kind of technical, kind of getting some stuff out of the way, because you'll see some things over and over in my presentation. I want to make sure we're all on the same page here. So one is, I'll show a few graphs, not a whole lot, but a few. And typically, almost always when I show a graph, the past is on the left and the present is on the right. So as you read a graph from left to right, any graph that I show today, this happens to be the global temperature since 1880, but the past is on the left, and that builds to 2020, the last year for which we have complete data, on the right. And so that's kind of how it works. One of the things, again, that climate monitoring branch does is calculate the global temperature using all of this information that comes in various forms from around the world. And so technically what this is, if a dot is above the line, that was a year that was warmer than the 20th century average for the globe. If a dot was below the line, that was a year that was below the 20th century average. And the zero mark indicates that year was the 20th century average. So all my graphs, past is on the left, present is on the right. That's how that works. And then I'm going to show a lot of maps, and they're very, very similar to weather maps that we see, except that weather maps are a specific snapshot in time. So they're either like the current conditions or the forecast 24 hours from now. And when a person in the climate services shows a map, it's really similar, but it's usually some kind of aggregation over time, right? So this happens to be the average temperature from the first 7 months of the year across the United States, just characterized as a color graph. And so that's just one subtle difference. When I show a map, that often in this presentation is not going to be a specific moment in time, but it's going to represent like either the average or the most extreme conditions over a slice of time. And so it's in many ways, many daily weather maps kind of stacked on top of each other and averaged into each other. And you'll be seeing quite a few maps. I just wanted to kind of get that little piece out of the way. And then, so finally, let's jump into normal. So we'll spend most of the rest of the hour that we have talking about the normals, the capital N normals that NCEI publishes, that you likely read in your paper as the context for today's weather, and very often mentioned in the nightly weathercast. Today's high was 87. The normal high for today is 82. Well, those normals come from somewhere. Turns out it comes from us. And we're responsible for making sure that they're the best values possible. And this presentation is to provide a little insight into how they're made, why they're used, how they're used, why do them every 10 years, what do we see when we change from one set of normals to the next, and so on. All right, I went to spent 12 years in Catholic school. So the first thing I got to do is a little confession. So I stole a lot of the following content from our normals team. So Dr. Mike Pilecki led the team. It's a group of several dozen, about 40 people ultimately involved with either a little bit at a time or a lot of the time, and kind of pulling the data together, running the algorithms, verifying the quality, making sure the format was okay, getting them in the hands of the Weather Service and the broadcast community. So a lot of people just spent several months putting this together, and I'm kind of ripping off their slides today. I want to acknowledge and just share with you like what a tremendous kind of team effort that is. It takes a lot of brains and a lot of sweat to get something that seems kind of simple out the door. All right. So, what are normals? What are we talking about? Again, this is an example of what you might see in a nightly weathercast. I grabbed these off of the Google machine. So this is the way a television meteorologist in Alpena, Michigan, where to characterize the weather in some November. I'm assuming November 2020, but it looks like it was a really warm stretch of days. So we're looking at a week of high temperatures in Alpena, Michigan in the 60s and 70s. And that's like, 20, 30 degrees above normal. So a really warm stretch of days in November. And that's one of the really nice uses of normals, right? It helps us compare what's happening today to some sort of expectations that of typicalness or normalness. And so the name normal is kind of means what it sounds like. What would be the average high or the expected high or a reasonable high for the day? And so being above or below normal, whether it's a day's temperature or a month's rainfall, that helps people give that first estimate of, is it getting it seems a little dry, and it helps put numbers on that. Seems a little warm for this time of year. Normals help you put numbers on that. All right, so here's what they are. There's a link at the top. This same link will be available at the end of the presentation as well. This is kind of where they're housed. Like, this is the official kind of first repository that everyone can come and grab and use from. And so again, it's that baseline for putting today's weather in context. I mentioned the two most prolific, or at least the most visible users, are our Weather Service uses these, are all throughout their products and services, and broadcast meteorologists. You'll often see this as well. But you'll also see these used when you look carefully among the kind of private sector and business interests across the country. So energy uses normals to help get a first order gauge on how much electricity will be demanded, say in Nebraska in July. Normals are the best first guess at how to plan for how much capacity and distribution of energy there's going to be needed. Likewise, the crop select, wow, another really big cloud to ground strike right out my window. Agriculture, the types of crops that we plant and when we plant them and how long we expect them to mature, those are based largely on normals and products and information that is derived from normals. You can say the same about the codes for construction and design. You know, how much freeze thaw, expansion, contraction do we need to build into bridges to accommodate both the day-night cycle and the year-long cycle of warming and cooling. Normals can inform that. And there's plenty of all of these industries, but that's just an example of kind of how they're used. They're this piece of infrastructure. They're a piece of the digital infrastructure of the United States that can kind of help us make more efficient, not just put today's weather into context, but to make decisions and more efficient decisions with the first order guess on what things are going to be. We're going to go over a little bit of what they're not just 30-year average. So, you know, in their simplest form, normals are 30-year averages, but there's a lot more to them than that. And we'll talk about some of the nuances, but ultimately what they're trying to represent are the average conditions of the last complete 30-year period, updated every 10 years, and some measures of how much the weather typically bounces up and down around those averages. But the normals that you see on the nightly weathercast, those are often, or at least now, if they're using the current values, based on the period 1991 through 2020. So that's the 30-year period that's gone into this latest batch of normals. Again, it's not just a straight 30-year average in most cases, but the basic concept is there. What are the average conditions over the last 30 years? Where do they come from? So this third set of bullets here, the Weather Service provides most of the information, the data that we inherit from the Weather Service, and that is the same weather information that they put into their forecast models that their forecasters use to analyze conditions. They have automated stations at airports, just automated surface observing systems and similar networks that report every hour automated. There are still thousands and thousands of cooperative observers, mom and pop type observers that go out and take a measurement of daily high and low temperature and or daily precipitation. Still thousands of people providing that vital service. Can't emphasize enough how important continuing those kinds of observations are for people like me who study and help people work within the climate. The fact that we still have thousands and thousands of those folks taking observations in a really similar way than they did maybe 130 years ago helps us make apples to apples comparisons by looking at those kinds of data sets and then seeing how these new, more modern data sets kind of behave around them. So we hopefully get a chance to come back and talk a little bit more climate science, but I can't emphasize how important it is to have that single point of structure through the observing system, those very precious volunteer observers. And then the COCO-ROS, the Community Collaborative Rain, Hail, and Snow Network, is kind of a modern instance of these citizen science folks, and building that next big database that's going to become more and more useful to climate science along the way. And for the first time, we were able to really richly incorporate this additional set of volunteer observer information into our normals. We borrow some snow and precipitation data from the USDA, wonderful partners of ours as well. So that's kind of where it comes from. And then NCEI, again, we're kind of the first dissemination point, but there's a lot of people doing really smart, neat things with us beyond us, of course. And then finally, I think this is about the last of the kind of conceptual, and we'll start looking at pictures here in a minute. But we publish these as annual, seasonal, monthly, and daily for temperature, precipitation, and snow. So what is the average temperature for the year? What is the average let's say low temperature for the season of summer. What is the average high temperature, the average afternoon temperature in July? And then what is the average overnight temperature on July 28th? So those are those kind of 4 scales there: annual, seasonal, monthly, and daily. We produce precipitation, temperature, and snow, a number of variables for each of those time scales. And that helps. For daily temperatures, it helps. You see that every day on the nightly news. Annual temperatures helps decide things like how much insulation do we build with? What are the codes that we build towards? How much sunlight or wind may we see over the course of a year? We also publish additional hourly normals. So this is by hour, by day, for temperature, dew point, which is a measure of humidity, pressure, air barometric pressure, clouds, and wind. We do averages. We do some cumulative year-to-date values. So how much rain would one expect by this date during the year or during the season, or how many growing degree days, which are important to agriculture, would we expect to see accumulate by this date during the growing season? So a lot of normals like that you don't necessarily see on the nightly news, but they're an important piece of the digital infrastructure. Counts and frequencies. So counting things that happen, like days over 90, days over 100, days below freezing, days with thunder, days with at least 2 inches of rain. Those types of counting and how often do we see these normals are part of the package as well. And then for the folks who use probability, who manage risk, the people that are making decisions based on how much risk can I take, and to help provide some measure of these averages, how much variability is around them, we divide history up into either 3 chunks, 4 chunks, or 5 chunks, which we call terciles, quartiles, and quintiles. So we'll go with the simple one there, the quartiles. That's what do we see, what is the top quarter? What are the warmest 1/4 days? Where's that 75% mark? That's a quartile measurement. We say, okay, the average value is here at 50%, meaning 50% of the time it's warmer or cooler than this, but we also provide the 25% and the 75%. And that helps people who are kind of doing a little more sophisticated calculations, assess what does that look like? How variable is the spread that one average is talking about? I think that's most of the kind of technical geeky speak, and we'll start looking at pictures here.
Deep, could I interrupt for 1 second? We've got some questions on the citizen science piece in particular. So we've got, first of all, a thank you for making the data available for download in CSV. And a question, do you ingest any of the data from the Citizen Weather Observer program?
CWOP. To the extent that is, I don't know how tied that is to the NWS Cooperative Observer Program. If there happen to be folks in the know, I can get back with you, Tiernan, and get back with Weatherband and kind of mention that after the fact, kind of follow up, and maybe we can put a little note on there, because I don't know for sure. I don't want to say it out loud. I appreciate it.
Yeah, no, we'd love to know more about the pathways that data takes when it goes into these different programs. So that would be fantastic. We can do some more follow up on that.
Yeah.
And then have you considered adding the number of days above IR equal to 100 degrees Fahrenheit, I believe?
I'm not quite sure what we're getting at with IR, but I believe days over 100, the concept is there. I know we have days over 90. I don't know if we include days over 100 officially. And I want to say, I think so. I think that's part of the mix. I can check real quick, maybe during the follow-up Q&A session, because I know where to find that.
All right, that sounds great. And then kind of going along, what techniques do you use for completing missing data?
Yeah, so we're just about to jump into that.
Okay.
Wonderful. Yeah, you bet.
Great. And then just another question, will you be covering sources of how methane is added to the environment? Or would that be a separate climate discussion?
That's a separate discussion. If we have time, we can talk. I mean, the short answer is some of the mechanisms where methane can get into the atmosphere are through kind of outgassing from warming oceans and tundra, and also some agricultural practices and leaks in kind of natural gas facilities infrastructure can all contribute to increased methane. And then just the general increase in kind of fossil fuel use and consumption, there's a methane association with that too. But we won't get into that technically here. No.
Got it. Thank you.
Yeah.
And then one more question.
Yeah.
Are there more temperate readings being taken from urban sites versus suburban? And what effect does it have on the new normals?
Yeah, that's a great question. We're going to jump into how we're going to touch on how we handle what we would call that a non-climatic bias. And we do account for those in both the global temperature, and we recognize those in the normals as well. And we'll get to that. That's on the docket for the next 20 minutes or so.
Fantastic. All right, we are all caught up on questions. Thank you.
Okay, very cool. So this is just a picture of what we've changed. And so on May 4th, we switched from the quote unquote old normals, which were newer than the older normals before that, to the new normals, which will be replaced sometime probably in the spring of 2031. But what we effectively did was the window of the climate that we were looking at was the blue box here, kind of stretching from 1981 to 2010. And we slid that window 10 years closer to the present and captured, we basically traded in the decade of the 80s and added on the decade of the 20 teens. And so the new normals represent kind of ditching that 10-year period represented by the 80s and adding this most recent decade. So the box that we're looking at slid from the blue to the red on that time. Why 30 years? There's a couple reasons that we use 30-year normals. One is that's about the amount of time that most of us spend kind of in our maturity professionally, right? So if we're a farmer or an energy professional or a gardener, typically, we have about we have about 30 years really in the business. So it matches with this kind of generational thing. So it appeals to our kind of professional memories. It is a tidy number. It's also the number at about which many statistical assumptions begin to become really valid. So having a sample size of 30 is a it's not absolute, but that is a generally accepted number that's a nice robust sample for most situations. So it helps to have at least 30. And then finally, it's as climate changes, whether it's due to long-term change, what we call climate change, or whether it's due to climate variability, things kind of bouncing up and down from decade to decade as patterns in the oceans and the atmosphere oscillate and move around. The last 30 years is a good first order measure of what we could expect in the 10 years going forward, the 10 years that these things are valid. And so this window kind of slides to keep up with what's going on with the climate system. And that's kind of why we use a 30-year period. There's a little bit of practicality too. That's a good coordination point. Most of the world's meteorological services aren't blessed with the depth of data and the rich history that many of us in Europe and North America have. And so kind of keeping us all, this is coordinated through the World Meteorological Organization. The normals themselves for the rest of the world are brokered through the WMO. We calculate our own here in the US. But the practice, to be able to say, what's your normal high? And that means the same thing in Tanzania as it does in Canada helps. It helps the meteorologists that share data and expertise and inform each other's forecasts to be on the same page. So there's a number of reasons on kind of why this process of updating every 10 years. So I gave the rationale for why we update it. The reason that we don't just kind of leave it in place is the climate is going to evolve out from under it. And we don't change it more often because changing the concept of normal every year is taxing, right? So, when we do the 5-year plan, the 10-year plan, the what kind of trucks should we buy for my fleet, the what kind of insulation should we establish? We want to know that these normals are going to be around long enough that we can adapt practices to them. So that's why we don't change them more often than we do, even though we're blessed with data now today that comes in near real time. And we could, conceivably do the math on that and make the computations, but changing to a new normal every year is really taxing on real people. So we're going to keep it at this every 10-year kind of cadence. So someone asked about, completeness of data. So in a perfect world, it's great. We have data for all days. And so this is Boston, headquarters of the AMS. So this is Boston International Airport. These would be the 30 numbers that would go into today's normal value for August 26th. So they're beginning at 1991 on the top and 2020 on the bottom. We're looking at maximum temperature, the afternoon temperature, minimum temperature, which is the overnight low, the amount of liquid precipitation that fell, the amount of snow that fell, and then the amount of snow that was on the ground. Obviously zeros for the snow in August, but wow, look at all those M's. Missing data, finds its way into the record. How does that happen? The world isn't perfect because stations move. Stations change instruments, technology changes, instruments break, instruments can kind of go haywire and bias warm or cold. The volunteers that take these daily readings can change from being an afternoon or evening observer to a morning observer, and that will affect the statistics of what they report. Whole stations break or get damaged, instruments break or bias. Volunteers break or go on vacation or are unable to take observations. And so accounting for these changes is an important and big piece of the work that goes into the normals. So for temperature, we do fill in the data that is missing. As long as we have a threshold amount of data, we'll fill in the data for missing observations. We'll draw from kind of neighboring station information, interpolated to the spot, some sanity checks as well. If there is too much data missing over the 30-year period, we won't be able to calculate a normal for that month. So, and this happens a lot in some of our mountain stations where there are observations either only for the cold and ski season or only for the warm season where the stations are accessible. And so we can only produce normals for those months that have kind of robust end-to-end. So that's the method that we fill in data. For the stations that have known changes in instrumentation or location or detected changes in station location or instrumentation, what we do is we find those change points and then we correct for them. And the normal that we publish is going to reflect the current station with the current configuration and the current instrumentation and the current observing practices. So our normals, when we publish them, are meant to reflect, if a station has moved or changed, it is the current day, present day station for which the normal is computed. And this comes into play because one of those decades that is in this normals data set, the 1991 through 2020, in the 90s, there were quite a few changes to the automated stations around the country. And some of those values from the early 90s in the kind of older station regime are included in the normals, but we make sure that those values that were measured in the old stations in the old locations are corrected to reflect what they would have been in the current locations with the current instrumentation. And that's, I hope that answers the question that they were getting at. There's a lot of work on how we do that. It's available, again, not just to continuously plug AMS, but the Bulletin of the American Meteorological Society really document. If you're a technical person, you really want to see the technical specs on that. There's an article by Anthony Arguez and co-authors. I think we'll have a link to it here in a minute that really explains kind of how we go through that. Monthly temperature data, that homogenized, that's the practice that I'm talking about, accounting for these discontinuities in the station data. So things that happen at the station level, a move, a change in instruments, a change in observing practices that would make a discontinuity among those 30 years. Homogenization is the term we use for correcting those biases. Monthly precipitation data, because precipitation is a much more local thing. It's much less robust to borrow from neighbor information. You can get away with that with temperature because temperature is largely a broad field. You know, if it's a warm day in Asheville here, it's going to be a warm day at the next town, Weaverville. And we know that we can borrow a lot of signal from that Weaverville observation and apply it to a missing observation here in Asheville. With rain, you can't do that. Rain is mostly a local event, especially for the eastern half of the country in the summer. These are convective storms that are local, and just borrowing numbers from neighboring stations is not the way to fill in missing data. And so if there's not enough data for a month, if there's not all days available for the month, we just won't consider that month being eligible to be in the normals calculation. There's an example here of a station in Dayton, Ohio that had some kind of changes in 2019 that caused the calculation of the normal to use a synthetic data set that had been adjusted to reflect today's kind of Dayton configuration. You can see a slight difference in the blue bar, which is the corrected data set, versus the orange series, which is the raw data set, which still has these inconsistencies. The raw data, of course, is kept. We don't throw away raw observations. Raw observations are super valuable. They're really important. We use them in the future. Other people use them to kind of grade our work to make sure that we're doing things the right way. So we don't change the historical observations, but we account for these discontinuities when we do the math to make the normals. And I see the Q&A's bumped up a little bit. Before I change gears here, Tiernan, did you want to jump in at all?
Yeah, thank you for pausing. So we've got some questions again on the data. How do you tell between the records which are representative for their region and those which only show ambient conditions?
So the normals ultimately are published at the station level. So they are representative of that station, much like when you hear on the evening weathercast, the high today at the airport was 73. The normal is calculated for that station. We do provide a gridded field as well, but the core bulk of the normals is to represent the conditions at that station. And in the context of the normals, if what the question is kind of getting at is urban heat kind of considered part of this? Yes, it is kind of left in there to the extent that if the current station has some urban heat signal in that, it is part of the normal construction. I hope that helps.
Yes, and if I'm not reading these questions right, or if you're not hearing, please put any corrections you'd like in the Q&A box. So following along on that, which elements are corrections due to relocation apart from temperature? So is precipitation, wind speed, radiation, cloudiness, etc.?
Yeah, so this would affect pressure. So pressure is very sensitive to the elevation of the station. I don't know the exact protocol. I'm more familiar. I've dealt more with the temperature over time, but that would be an example of a variable that would be affected by a station move. A station's elevation, even if it moves a short distance, if it goes up, 5 or 10 feet in elevation in the process of that move, which is really easy to do in a mountainous area, the pressure at the new location the pressure at the old location would need to be adjusted to represent conditions at the new location. Not sure that's happening for wind. In fact, I'm positive it's not.
Got it. Thank you. Yeah, we had a lot of questions on how to site your weather stations during our instrumentation series. So
Okay,
this is really a fantastic follow-up for that.
awesome.
And then the last question that we had open right now, how does all of this data affect the adjustment of planting zones, and how often does the adjustment of planting zones occur?
I am really, really glad you asked. That's coming up very soon. That's my
Okay.
only animation in the whole presentation.
Oh, exciting.
Awesome.
All right.
All right, great preview. Thank you. All right, so this is the article where you can get the technical specs on what happens when these adjustments are made and why we do that, and a lot more technical background on what is normals. All right, so this is an example of the gridded product. This just happens to be the normal temperature for March and the normal precipitation for March. So this is after all of those adjustments have been made in the temperature field at the station level. We then grid that, provide like a nice smooth, every pixel on this image is a 5 kilometer by 5 kilometer pixel. No surprises here. It's warmer in the south than during March. It's wetter in the southeast during March. So this is and it's very active precipitation along the Pacific coast and those upslope events, the marine borne events that provide the wet season along the Pacific coast. So you can really kind of see a picture of where the most rain falls from a total numbers standpoint. A lot of the folks on the upslope side of the mountain ranges in the Pacific, and particularly the Pacific Northwest, get a lot of March precipitation from those moist westerly winds that howl in that part of the world and get strained out by the mountains. And then obviously the region, as the region taps into the Gulf moisture, you kind of see that as that bullseye kind of emanating from the deep south. So that's an example of what the normals will look like. We have those again for every month. There are station values for every day. And we won't go into every single month. It is available on the web to be able to kind of explore the normals. Yeah, what are the new normals? Man, I can't type. What do the new normals say? So just to recap, we had about 15,000 stations that provided precipitation information that we were able to make normals out of. And we had about 7,300 stations with temperature normals. I got the bullets kind of reversed here. The warming, the general warming that we saw during the course of the decade, again, 2011 to 2020, were the new years to the normal, replacing 1981 through 1990. For most places, the most recent decade was a lot warmer than the 80s. And so we see that reflected in most of the country, but not everywhere. And that's like a recurring lesson in climate monitoring and climate analysis is the global temperature is going up, but that is a global average, and you have regional and seasonal counter trends to that. Certainly shows up in the normals, and we'll look at some of those. Generally speaking, the precipitation is a noisier field to begin with. The changes from one set of normals to the next was likewise noisy. But generally speaking, kind of the eastern and central US, particularly more adjacent to the Gulf of Mexico, it's getting wetter over the course of the year. The eastern US becoming a wetter place. Here's some examples. So we got 4 maps on here. The 2 on the left show the change in normal precipitation for the month of April. One's expressed as a percent, how many percent bigger is the new value. One's expressed as, actually how much bigger is the normal in terms of inches. But you can see that the wet part, the southeast United States is got wetter from one set of normals to the next. Proportionally, Montana and the Northern Rockies, they added a little rain, but that's a pretty dry place and not a particularly wet month for them. So it bumped the percentage way up. So while it's not as dramatic on the bottom map, because the baseline was lower to begin with, just a small increase in precipitation up there kind of shows up as a big change in percent. The Southwest, April got quite a bit drier. Again, from a very dry baseline to begin with, we saw April get drier. But that's a good example of the really mixed patterns that you can see in the precipitation field in almost every month. There's not a real big monolithic change in any month. Precipitation changes and precipitation behavior in the climate system in general. There's a lot of kind of spatial patterns, wet, dry patterns, and that showed up in the normals as well. These are real signals. It definitely did get wetter. It's just there's regional patterns to where we did get wetter. April was one of the months where we saw the northern plains get quite a bit cooler. April and then some of the winter months in the northern plains, we did see them cool from one, meaning that this most recent decade was generally cooler than the one that it replaced. Particularly in the afternoon temperatures. One of the kind of truisms that holds true in kind of a 3 out of 4, 4 out of 5 kind of way in climate is the minimum temperature tends to be warming faster than the maximum temperature. Overnight lows, the cooler times of day, the cooler places, and the cooler times of year are typically warming a little faster than the warmer places, the warmer times of day, and the warmer times of year. So you can see that the blue is a little more vivid in the afternoon temperatures in the northern plains. I think that's really kind of telling. But again, generally speaking, we'll kind of look across the year. But generally, most of the country got warmer into April. April and February, I think, had the most blue on the map, the most representation that the normal actually decreased. And those were both mainly in the northern United States. These are the fall months. So October, November, December, the last quarter of the year, you can see kind of a yo-yo effect in the Southeast. So October and December got quite a bit warmer from one set of normals to the next. So again, the new decade bumped October and December, particularly in the Southeast, the Midwest for December, big time changes. So December became or was a lot warmer place in the most recent 10 years than the previous set of normals. But November, again, kind of just the opposite. November, because of those new 10 Novembers that were added into the mix, and partly because of the 10 Novembers that were taken away, the Southeast has a slightly cooler baseline for afternoon temperatures in November. We could go through these maps kind of all day, but they're kind of out there through our Cooperative Institute success and have published quite a bit of these. Again, I just wanted to highlight, this is minimum temperature for Harris County, Texas, which is Houston. And the red curve happens to be the 10 years that were added, that were new to Houston. So this is minimum temperature. I believe I added July and August in here to just, the minimum temperatures. And then the blue temperature isn't the old normals. It's basically the last half of the 20th century. And this is the distribution. So as we look at this, it's cooler on the left, warmer on the right. Where the bar is higher, whether it's a red bar or the blue bar, that means that period, that's where more of those values show up. So you can see like a peak here around 77 degrees. Overnight lows is kind of the most common overnight low for the 2010s. And then for the late 20th century, the most common value was kind of like more like 70, 74. So that's a pretty significant difference in a decade. This is an extreme example. Houston summer and minimum temperatures are changing kind of faster than the rest of the baseline. So this is a little more exaggerated than what we see everywhere. The only reason I put this in there is we often talk about normals as one number, and what they represent is a range of possibilities. And I don't know if you can see my mouse, but I'm tracing over this red curve. They aggregate many different outcomes. They don't all land on the same number. The normals represent the middle point of a distribution of values. And that's kind of what one of the things that's not readily apparent in the climate system. The normals are that middle value, that one value. If you were going to pick a number out of a hat, this would be the one that you would get for like what's going to be high temperature for my kid's wedding in 3 years. Well, who knows? That's dependent on the weather. But if you absolutely had to pick a number, you would go to the normals, and it would be the number that's in the middle of this distribution. But the distribution itself would say it could be, a large range on either side of this. I hope that helps. This is very quick to just kind of run through this. These are some Midwestern cities. Again, most of the Midwest is getting warmer over, or at least warmer. They are warming over time, and the new normals are warmer. Again, the minimum temperatures, the overnight temperatures are changing just slightly more than the afternoon or high temperatures. This is for the Southeast, kind of a similar thing. Again, the minimum temperatures, the pink numbers on the right, on average are just a bit larger, meaning a slightly larger change, a slightly larger warm change than the afternoon temperatures, and kind of unanimously getting wetter throughout the year in these southeastern. So the green values represent how much wetter the new normal is, the cumulative normal for the year is. And then just some changes for kind of around the country. And again, most of the country getting warmer. A small piece of that north central US represented here by Fargo did cool slightly. And then kind of a distribution of the precipitation. You can see some significant changes. Asheville, where I live, wettest decade by far, crazy wet decade, lots of rain here. And our normal went up by 4 inches, just by swapping out one decade for another. And then, just the general picture. So this is looking at all 12 months. The change in all 12 months collapsed into one map that represents the change for the average over the year. Again, wetter, generally east of the Rockies. Generally speaking, drier west of the Rockies and in the desert Southwest. Most of the U.S. Got warmer. Again, the northern plains stayed flat to slightly cool. Those were the changes that we saw from one normal set to the next. They reflect pretty much what we expect in a warming world. In a warming world, taking a big 10-year chunk, we're going to expect most of the country to have been warmer in the most recent 10 years than the 10 years that's rolling off. And that's what played out in the US. That's just comparing that moving 10-year window. When we go back and compare the latest normals to the average for the whole 20th century, instead of just this 10 years at a time moving window, incremental changes, this is more like the cumulative change that we've seen. So how do today's normals, 1991 through 2020, stack up against the 20th century? And that's where the signal becomes really clear. When we look at that long-term signal with climate change, and normals aren't really the tool that we would use to measure climate change. They just can reflect the climate change. But the east of the Rockies has gotten a lot wetter. The new normals are a lot wetter than the kind of historical 20th century average. And almost all of the country is a lot warmer in the new normals than the 20th century average. This is what we would have published as normals if we use today's methods and all of the data that we recovered from today over time. And so you can see, these play out. The second graphic here, the teens, 20s, and 30s, a very kind of dry set of decades there. So that was kind of the driest normal that we saw from most of the country. The 40s, 50s, and 60s, the upper right set of normals, really dry in the Southwest. You can really see the wettening of America in the late 20th century as reflected in these kind of marching 30-year normals, culminating in that graphic on the bottom right, which is the same graphic that we looked at in the previous slide. Much of the US a lot warmer or a lot wetter than the 20th century average. And then finally, the same, we can really see the last 50 years or so, the warming, the long-term warming that we've been experiencing for most of the last 100 years, but especially since the mid 20th century, really manifest in those last maps that are quite a bit redder than the maps before them. There's a whole article in that link that it kind of explains this. Snowfall is always a mixed bag. It's a tough thing to measure. It doesn't happen very often, and it's not easy to measure. So snowfall usually sees kind of the most noise in climate data sets in general, but also in normals. Snowfall increased slightly in kind of the Great Lakes adjacent parts of the Midwest, and decreased in kind of the warmer parts of the Midwest. And then finally, we'll kind of rapid fire, bam, 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 through the degree days and get to questions. So degree days are heating degree days, are kind of a little bit opposite of what they sound like. They represent kind of coldness. The number, it basically represents the amount of energy that we would have to use to bring indoor temperatures up to a comfortable level. So the colder it is for the longer amount of time, the more heating degree days you're going to pile up. Heating degree days have generally kind of reduced in one set of normals to the next, meaning a warmer baseline, less heating needed to bring temperatures up to a comfortable level. So kind of a cost savings from that perspective. On the opposite, cooling degree days, representing kind of the cumulative amount of energy that we need to bring temperatures down to a comfortable level, have really shot up in almost all of the country. You can see the patterns that looks like much like we saw. So not a big increase in cooling degree days in the northern plains, but where we saw the country get a lot warmer, we're basically investing a lot more energy into keeping things cool. So this is part of the energy mapping of the U.S. You know, energy companies, energy consumers are sensitive to this and are tied to this. This basically means during the warm parts of the year, when we need to be cooling our homes in places that we need to cool our homes, we're typically spending more energy to do that. And then finally, growing degree days. And every crop has kind of a different baseline, but growing degree days are kind of a cumulative measure of warmth. And some row crops really, you know, they need a certain number of growing degree days or cumulative warmth to come to maturity. And generally speaking, the new normals reflect that those things are happening. You know, we're getting more of those. And so a corn crop that needs X number of growing degree days to come to maturity in a typical year in the new normals, that is happening. They're getting to that number faster than they used to be. And I'll stop there. And here's the animation for the horticultural zones. So you can see this is just cycled through a few times. So it starts with the old normals, you kind of see the new normals, and then we kind of zoom in on the change of that. And the gist of it is, for much of the eastern US anyway, the planting zones crawled, 50 miles or so northward or upward in elevation as we went. So the new normals kind of feed into this in a way. These are really sensitive to what is the coldest temperature of the year. And so that aspect of the new normals works its way into that. So generally speaking, a warmer country means that the growing zones are kind of crawling north. That means growing conditions are traveling a little more north, and the weeds and the pests and the good plants are all migrating a little north as well. And I'll stop there. We talked about growing, heating, and I'll stop there. So that those last two slides are a little redundant, and we can answer questions, hopefully. So Tiernan, I can't hear you, so I'm just going to start reading them off. I think you may be on mute. A question here, it says, we measure temperatures to the nearest degree Fahrenheit. Why do we not calculate, or what would it not be precise to, where are we getting that 1/10 of a degree on average? And that's a great question. In general, the daily values that we publish, they are rounded kind of back to that whole degree because they're a little more relevant one-to-one. When we're talking about monthly, seasonal, and annual averages, it helps to get that that extra decimal point in there. It's completely statistically kind of the logical thing to do. We benefit from the statistical power of a large number of samples. In football, we see this. A running back will only gain yards in whole chunks. He may gain 2 yards, he may gain 8 yards, he may gain -3 yards. We measure that in whole chunks. But the rushing average is typically reported as like 4.3 yards per carry. And we can do that with signal and confidence when we have enough samples to get that extra piece of information. And so as we measure normals and calculate normals over longer periods of time where we have more of these days feeding into those normals, it totally makes sense to gauge things down to that decimal point, because then we're talking about subtle things in climate, not necessarily daily high temperatures. We're talking about the subtleties of average conditions over time. And that becomes, much more meaningful. And we will and will continue to throw in those decimal values. Got a question, how do extreme events like the big rain in Tucson affect the next 10 years? That will show up in the new normals. So big, gigantic events are not erased or lessened. They are part of the data set that feeds into our understanding of the current climate. And so that big Tucson monsoon event from this July and August, that will be one of the 10 new years that is added in the next round of normals. And all else being equal, they will have a tendency to pull those normals to the wetter side for those months. In the 20th century, station networks were not as dense as today. So how were the 1901 to 2000 normals computed? The 1901 to 2000 normals aren't normals. That's one thing. Those are averages where we've gridded the stations that we've had and applied those to 5 kilometer by 5 kilometer grid. So we don't publish those as normals. Those are comparative. That's a comparative period, kind of using similar methods. Again, for temperature, using information from neighbors, it is much, temperature is a field that behaves in kind of, it's big and slow. If it's a hot day in Oklahoma, it's very likely a hot day in Arkansas. And so we're able to extrapolate a little more confidently in data sparse areas with temperature. For precipitation, part of the noise that we see in those maps very much reflects the fact that we don't have, there are areas that are less densely observed. We do have more precipitation observing stations than temperature stations, particularly over time. But for the big picture averages, especially for temperatures, we have plenty of data to make characterizations of bigger spatial scales. And I think those were the most upvoted. Yeah, I think that's it. And Tiernan, I don't know if we lost you along the way.
I apologize. My internet did go out.
Okay.
All of a sudden, but thank you for continuing on without me.
Yeah, you bet.
There was one other question. I don't know if you saw it, if you could comment on trends at individual sites. Did you see that one?
Yeah, and I think this is kind of in the same spirit as the last one. It's kind of, what do we do with weird things that happen at stations? And for the station normals themselves, again, we want to, when we detect those changes and we observe those changes, or we know about those changes through the metadata associated with the station, we move the station from here to here, we change the instrument from this to that. But we also have algorithms that look at the station's history, say a change happened here. So in the normals, we want that adjustment to help bring the record to what would today's station have observed over that 30-year period. Now, if this is kind of getting at what do we do kind of in the context of measuring climate change, we remove those biases of the urban heat island or stations moving. We again tend to correct towards today's values, but we do not, like the urban heat island is almost entirely detected and corrected. in the global kind of in the measurements that we take that go into computing the global temperature. I think that's what the question, and there was a couple similar questions, and I think this questioner is kind of getting at that same point. So if that's what you're getting at, I think that's what you're getting at, and that's what we're doing.
Fantastic. Well, thank you so much for this wonderful presentation. I really appreciate you walking us through this and giving us such an informative. With that, again, just please come over and continue the conversation on the AMS Weather Band community. We'd love to see you over there. And this video will be posted up there in the next day or two, so you can continue to learn and revisit and share. So thank you again so very much. We really appreciate it.
Thank you. And we do share with Environment Canada. Yes, I saw that the question just jumped in there. We collaborate with our friends north of the border. Right.
Excellent.
Thank you. Thanks for having me.
Thank you all. Yeah.
All right. Awesome.
Thank you all so much for coming, and have a wonderful rest of your day.
All right.